There will be 4 free response questions on the AP Precalculus exam. This video is modeled after FRQ 2. It's about exponential modeling and average rate of change. Let's pretend it's from the 2005 AP Precalculus exam. If you appreciate the content, please give it a like. Overnight, a large snowstorm passes through Plugtown. Snow began falling at 12 a.m., t equals 0, and continued to fall until 6 a.m., t equals 6. Once the snow stopped falling, Mr. Passwater began shoveling the snow off his driveway. By 9 a.m., t equals 9, only 25 cubic feet of snow remained on Mr. Passwater's driveway. The amount of snow on Mr. Passwater's driveway in cubic feet can be modeled by the continuous piecewise function s given by this piecewise expression, where s of t is the amount of snow on the driveway in cubic feet at time t hours since snow began at 12 a.m. Part 1. Use the given data to write 2 equations that can be used to find the values for the constants a and b in the expression for s of t. Be careful, a and b appear in this part of the piecewise function, so I need to be sure to use values of t greater than or equal to 6. In other words, we cannot use this first data point that at time t equals 0 there was 0 snow. I need to start with t equals 6. We are told that at t equals 9, there are 25 cubic feet of snow on the driveway. So we have the input-output pair 9, 25. We need to know how much snow is on the driveway at time t equals 6, but they don't tell us directly. However, they do tell us that this piecewise function is a continuous piecewise function. Notice that t equals 6 is the transition time from the first piece of the piecewise function to the second piece. Because the piecewise function is continuous, the value of both parts must be equal at t equals 6. For that reason, we can use the 70t part to find the amount of snow at time t equals 6. So at t equals 6, 70t becomes 70 times 6, which equals 420. Each input-output pair can be used to write an equation. If we plug in 6 for t, the output value should equal 420. So this expression becomes a times b to the 6th power is equal to 420. The second input-output pair will give us a second equation. If we plug in 9 for t, it should equal the output value of 25. So the second equation is a times b to the 9th power is equal to 25. So that's the answer to A part 1. A part 2. Find the values for a and b as decimal approximations. I'm going to show you how to find a and b 2 different ways. First, I'm going to show you how to do it mostly by hand. Then I will show you how to use the regression capabilities of your calculator to find a and b. The reason why I have to show you how to do it by hand is because you can only do exponential regression when the given model is exactly a times b to the t power. That is what we have, so that's why we can do regression. But very often you will be given a variation of this that might be something like a times b to the t plus 1 power, or it might be a times b to the t over 12 power. If it's a variation like this, you cannot use the regression capabilities of your calculator, and you have to do it by hand. So that's why I want to show you how to do it by hand first. Let's start with the first equation and get a by itself by dividing both sides by b to the 6th power. That will give us a is equal to 420 over b to the 6th power. Now we have an expression that we can plug in for a in the other equation. So we will have 420 over b to the 6th power. Okay, I'm putting that in for a, but that will be times b to the 9th power. I'm going to write it as b to the 9th over 1, just to make it clear that this is in the numerator while these b's are in the denominator. This is all equal to 25. On the next step, the 6 b's in the denominator will cancel out 6 of the b's in the numerator, leaving behind 3 b's. So on the next step, we have 420 b to the 3rd power is equal to 25. Dividing both sides by 420, we get b to the 3rd power is equal to 25 over 420. To cancel out the 3rd power and get b by itself, we can raise both sides of the equation to the 1/3 power, like this. On the left side, the 3 times 1/3 is 1. They basically cancel each other out, leaving b. On the right-hand side, we have all of it. So b is equal to 25 over 420, all raised to the 1/3 power. Now we will need the calculator. We're just going to type in this expression to get the decimal approximation. Always reset your calculator at the beginning of an FRQ by hitting second plus 712. Again, that is second plus 712. Fresh calculator. We need to open some parentheses, and now we need a fraction. If your software is up to date, you can hit alpha x. Otherwise, you have to hit alpha y equals enter. It's 25 over 420, and then all raised to the 1/3 power. So exponent, another fraction, and 1/3 power. And hit enter. The College Board will accept 3 decimal places. However, students will often try to round to 3 decimal places, and then they round wrong. So my recommendation is always use 4 decimal places and don't try to round. So let's write 0.3904. Kabam! Also, let's go back and store this value into a letter on the calculator. So immediately hit the store button, and we want to store this into letter B since this is B after all. So just hit alpha B and hit enter. Now we can go back and find the value of A, which is 420 divided by B to the 6th power. So fraction mode, we need 420 divided by, since we stored all of these wonderful decimals into letter B, we can use B now by hitting alpha B and then to the 6th power. Never use an abbreviated value. If you type in 0.3904, okay, a shortened value, your final answer is going to be off, and you are likely to lose a point because of a rounding error. Instead, store all of the many decimals into letter B, and then do 420 over B to the 6th power like this. And hit enter. Okay, I'm getting this weird fraction right here. We really want a decimal approximation. So I'm just going to turn around and divide this like, so I see we have 592,704 divided by 5. Okay, so there's my decimal approximation. A equals 118,540.8. So that is the answer for A part 2, and that's how you find A and B, mostly by hand. Now I'm going to show you how to find those values even faster using the regression capabilities of your calculator. So we begin by essentially typing in this table into the calculator. Actually, before we do that, I want to show you how to type in the exponential model as y1 on your calculator. Remember that we stored the value of b into letter b. Let's also store the value of a into letter a by immediately hitting store and then alpha a and enter. Remember that the exponential part of our model is a times b to the t power. Let's type this in as y1 on the calculator. Hit y equals, and because we stored the values into the letters a and b, we can literally just type a times b to the x power, like this: alpha a, alpha b, raised to the x power. We will need this equation for later problems in this FRQ. Now let's start over and find the value of a and b using exponential regression. Hit the Stat button and immediately hit Enter. We need to type in the input values in L1 and the output values in L2. So we will type in these values in L1 and these values in L2. To find the values of a and b, hit the Stat button. This time switch to the Calculate menu. Scroll down to option 0, which is after the number 9, and you will find Exponential Regression. So we can choose this. Next time, if you remember it, you can just type the number 0. Anyway, always tell your calculator to store the regression equation in y1. So come down to here and type in y1 by hitting alpha, trace, enter. Now just hit enter a couple more times and the calculator will give you the values of a and b. Kabam! Notice that these are the exact same values we found by hand. Also notice that since we told the calculator to store the regression model as y1, it's typed in for us. B part 1. Use the given data to find the average rate of change in the amount of snow on the driveway in cubic feet per hour from t equals 6 to t equals 9 hours. Express your answer as a decimal approximation. Show the computations that lead to your answer. The average rate of change of s on the interval from 6 to 9 is given by s of 9 minus s of 6 divided by 9 minus 6. It's just the average rate of change formula. You have to show this setup to get credit. S at 9 is 25, and S at 6 is 420. Of course, 9 minus 6 is 3. I'm just going to type this into my calculator right now. Okay, I'm getting this little fraction again. I'm going to go ahead and do negative 395 divided by 3 to get my decimal approximation. Negative 131.6666. Use 4 decimal places, don't try to round. Let's define a letter C as being equal to this average rate of change so that we can use the letter C in our calculations later. Let's store this value into letter C on the calculator as well by hitting store and then alpha, C, and enter. So the answer to B part 1 is negative 131.6666 cubic feet per hour. However, it is probably safest not to include the units on this question because you can earn the point without any units. However, if you accidentally put the wrong units, you will lose the point. So why risk it? B part 2. Use the average rate of change found in part 1 to estimate the amount of snow on the driveway for time t equals 7 hours. Show the computations that lead to your answer. Here's a graph of the piecewise function s of t, modeling the amount of snow on the driveway over time. The first piece of the piecewise function models the accumulation of snow on the driveway, as snow began to fall at time t equals 0 and stopped falling at time t equals 6. During that interval, snow fell at a rate of 70 cubic feet per hour, and we went from no snow to 420 cubic feet of snow on the driveway. The second piece of the piecewise function models the time where Mr. Passwater was shoveling snow off of the driveway. In B Part 1, we found the average rate of change of the amount of snow on the driveway from t equals 6 to t equals 9 hours. This average rate of change is the slope of the secant line of s of t from t equals 6 to t equals 9. When they ask us to use the average rate of change to make an estimate, they are really asking us to write an equation for this secant line and use that equation to make the estimate. We can write the equation of the secant line in point-slope form as long as we have a point, which will go here, and the slope, which will go here. For the point, we can use either of the input-output pairs that we used to calculate the average rate of change. The slope is the average rate of change itself that we called c. I'm going to use 9,25, but you would get the same answer if you used 6,420. So the equation is going to be in this form. We write y minus y, so y minus 25, is equal to the slope, and we can just use the letter c since we defined the average rate of change as c, and then times t minus t, so t minus 9. Right there, this is an equation for the secant line, but since we need to use this equation to make an estimate, it will be better if we get y by itself. So let's add 25 to both sides. So we will have y equals c times t minus 9 plus 25. So this is the equation of the secant line, and we will use this equation to estimate the amount of snow on the driveway at time t equals 7 hours, which is like right here. Okay, so we're going to be finding this point on the secant line. So we will show this by writing y at 7 using this notation. Means that we are about to plug in 7 for t. I'm going to erase some of this. I need space. We get y at 7 is equal to c times 7 minus 9 plus 25. Obviously, 7 minus 9 is negative 2, so we can write y at 7 is equal to negative 2c plus 25. Let's type this into the calculator to find the decimal approximation. Remember, we stored the average rate of change, the slope, into letter C on the calculator. So we can simply type negative 2c plus 25. Kabam! 288.3333. At t equals 7 hours, there are 288.3333 cubic feet of snow remaining on the driveway. However, it's probably safest not to write the units. You can earn the point without units, and if you accidentally put the wrong units, you will lose the point, so why risk it? B Part 3. Consider the average rates of change of S from t equals 9 to t equals p hours, where p is greater than 9. Are these average rates of change less than or greater than the average rate of change from t equals 6 to t equals 9 hours found in Part 1? Explain your reasoning. In Unit 1, we learned that wherever S of t is concave up, the average rate of change of S of t is increasing. We learned that any interval where s of t is concave down, the average rate of change of s of t is decreasing. Since s of t is concave up for t greater than 6 hours, the average rates of change of s of t are increasing. Therefore, the average rate of change of s of t on the interval from 9 to p is greater than the average rate of change on the interval from 6 to 9. By the way, including a detailed graph like this one can often save you a point in case you leave out a detail in your explanation. But your graph has to include labels and numbers like this. Caution! To earn the point, you have to be specific. Say s of t is concave up. Don't say the function is concave up, or the graph is concave up, or worse yet, it is concave up. You have to say s of t. Also, don't simply say the average rate of change is increasing. You have to say the average rate of change of s of t. Be specific. Part C. Mr. Passwater plans to shovel snow until there is no snow left remaining on his driveway. Explain how this information can be used to determine the domain limitations for the model S. Since s of t represents the amount of snow remaining on the driveway, normally we would use our calculator to find the time when s of t is equal to 0. Let's call that t equals c for now. Since Mr. Passwater plans to stop shoveling snow when s of t is equal to 0, the domain should be from 0 to c. However, that doesn't make sense for this problem, because for time t greater than 6, s of t is an exponential decreasing function that approaches 0 but never reaches 0. Mr. Passwater plans to stop shoveling snow when s of t is equal to 0. However, this will not lead to a domain limitation for s of t because for t greater than 6, s of t is a decreasing exponential function which approaches 0 but is never equal to 0. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.